Hello again, everyone. Mr. Cruze here with another Algebra 2 review for you. This time, the final exam review, part 2. Alright? We're going to continue on and do as many problems as we can in this review. At any time, if you have any questions, you can always email me, tweet me, post comments in the video. I'm here to help you as best I can, alright? So, let's get into it. Graph y equals the square root of x minus 3. Now, I just make t-tables for these. I start off with square root of x. And what are the basic numbers I can take square roots of? Well, the first one I can do is 0. Obviously, anything in the negatives isn't going to fly because we'll get imaginaries. And we're not graphing imaginaries, okay? So 0 is the first one. Square root of 0 is 0. Next one I could take a square root of nicely is 1. Square root of 1 is 1. Okay? The next one would be 4, and the square root of 4 is 2. Alright? But unfortunately, that's not the one I want to graph. I want to graph square root of x minus 3, right? Well, since this minus 3 is in there with the x, I'm going to take the opposite of what I see. This tells me to add 3 to all my x coordinates. You take the opposite whenever it's with the x, alright? And that goes for these as well. So, basically it means I'm moving everything to the right 3 units, okay? So when I add 3 to my x's, 0 plus 3 is 3, 1 plus 3 is 4, and 4 plus 3 is 7. Notice there's nothing being added or subtracted on outside, so the y-coordinates actually stay the same. If you want to plug these numbers in and check me, you can. But anyway, now we can graph it. 3, 0, 4, 1, and 7, 6, 7, 2. And then there's your graph. It kind of looks like half of a sideways parabola. Alright? Oh, I could do a better job than that. There we go. Notice it does not go down here at all because that's kind of the starting point. You can't go any further the other way because you'll end up with negative under the square root, and that can't work. Graph y equals 3 to the x. Again, make a t-table. For these, though, you can really plug in any x value. The domain is all reals. I usually go with negative 2, negative 1, 0, 1, and 2. And then you just plug those in your calculator. So you do 3 to the negative 2, and you get 0.1 repeating, but really, with our graph here, 0.11 will suffice. 3 to the negative 1 is 0.3 repeating. 3 to the 0 is, of course, 1. 3 to the first is 3, and 3 squared is 9. Notice there's no shifting, no moving thanks to the x, and there's nothing being added or subtracted at the end. So this is just graph as it is. Negative 2.11 is right there. Negative 1.33 is right there. Do the best you can as far as approximating it. 0, 1, 1, 3. 2, 9 is going to be somewhere up here. So you kind of get the basic shape of what's going on here. Any of your exponential graphs should look like this. If it's decay, it'll kind of look like going down this way, okay? Write an exponential function to model the situation. Find the amount after the specified amount of time. 95,000 population grows 2.3% per year for 12 years. This is just basic exponential growth. So you're going to use the formula y equals ab to the x, where a is your initial amount, how much you start with. B, since you're growing, B is going to be 1 plus your rate, okay? If it was decaying or going down, it would be 1 minus your rate. And then x is time, of course. So let's get our equation. Our initial amount is 95,000. B is 1 plus our rate. Well, our rate is kind of here, only instead of 2.3%, I have to convert that by moving the decimal point 2 places to the left. So it's actually 0.023. When I add 1 to that, it's 1.023 to the x. So there's our equation. And then they say after how many years? 12 years. So let's plug in 12, okay? So you go to your handy-dandy calculator, and you take 1.023 to the 12th power and multiply that by 95,000. And if you do things correctly, you should get 124,804, 0.777, but I can't have 0.777 of a person, so there is no rounding up here. It's just 124,804. All right. 16 for the rate of change. Find the corresponding growth or decay factor plus 70%. Here's really what they're doing, folks. They're asking for B. That's what they're asking for. Same thing as here. Well, it's positive 70%, which means we're growing. So you're going to do 1 plus your rate. Well, 70% as a decimal is 0.7, so that'll be 1.7, okay? 17, find the amount of continuously compounded. Whoop, that should be sounding some alarms. Continuously compounded means you're going to be using this formula, A pert. Any of the ones you have continuous compounded, it'll be A pert. Oh, looks like they're trying to shut me down here. Abort. Abort. Why is it not aborting? Okay, there we go. A pert. So P is your initial amount this time, 2,500. E is a number on your calculator. R is this just as a decimal, so 0.053. You do not add 1 this time. And then times T is 5 years. And then you just kind of plug that in your calculator. I do it in one step as far as the E part. I make sure when I type in E to the, and then it gives me a parenthesis, I put it all in at once, okay? That way you don't have to worry about messing things up as far as the calculator is concerned. So when you do this, you should get $3,258. And since we're talking about dollars and cents, we can go ahead and do 58 cents. If you do not get this, I suggest you ask. That way we can help you use your calculator, all right? 18, half-life. Oop, I remember the half-life formula. A times 1/2 to the T over HL power, okay? Where A is your initial amount. Let's see. Half-life of phosphorus 32 is 14.3 days. Write the exponential decay function for a 50 milligram sample. Half-life is always a half, so that's nice. T over, well, what was the half-life? 14.3 days. Boom, there's the function. Then find the amount after 84 days. So we're going to plug in 84 for T, okay? But they could really ask us at any given time. So again, I would take 0.5 to the parentheses, 84 divided by 14.3, and then multiply that by 50, and you should get 0.852, and these is in milligrams remaining, okay? Which makes sense, because it went through quite a few half-lives, so it makes sense that it's down that low. 19, evaluate the logarithm, log base 64 of 1/32. Now, unfortunately, my calculator, and probably yours, can only do log base 10. Can't do log base 64, so how do I do that? Well, there's a nice little formula. If I have log base m of n, then that's actually the log of n divided by the log of the base. So you can really do that for anything. So you can do log of 1/32 divided by the log of the base, log of 64. By the way, in case you're curious, you can actually do natural log as well if for some reason you prefer natural log. They give you the exact same answer as long as you type things in your calculator correctly. I get negative 0.833, and it just continues on in that pattern. Okay? But anyway, you should get that as an answer. Again, if you don't, let me know so I can help you with your calculator. Write the equation in logarithmic form. 10 to the third equals 1,000. Well, logarithmic form means I need to log both sides. Fortunately for us, normally we'd have to log and then do whatever base this number is here. But since it's 10, well, it's log base 10, so that's quite nice. The log and the 10 cancel each other out, and you're left with 3 equals log of 1,000. And this is logarithmic form. Basically, instead of having exponents, now you have logs, okay? There are other ways to do it. This is the way I do it. Just log both sides. Technically, the 3 comes out front, which is why you have the 3. And so that's what it is, logarithmic form. If you wanted to go backwards to exponential form, you would bump the base, right? You'd make that 10 and then 10. So 10 to the third would equal 1,000, which is what we started with, okay? They just kind of undo each other. 21, this is probably the bear right here. Graph y equals log base 7 of x minus 2. I'm actually going to go to a different sheet here to do this one because I want to make sure we have enough room for it. Y equals log base 7 of, what was it? I think it was x minus 2. The way I do this is I switch the x and y, and I'll show you why here in a second. Haha. I bump the base since it's 7, so it'll be 7 to the x equals y minus 2. Then I add 2, 7 to the x plus 2 equals y, okay? I just rearrange this. This is actually the inverse of what we started with, okay? And the cool thing about inverses is if I can graph the inverse, I can flip the x and y's to graph this. So I'm going to make a t-table for this now. So let's make a t-table for 7 to the x. Again, just like we did before, we do use -2, -1, 0, 1, and 2. 7 to the -2 is like point, let's see, 0, 2, 0, something like that. 7 to the -1 is 0.143. 7 to the 0 is 1, 7 to the first is 7, and 7 squared is 49. Now, this plus 2, notice it's not with the x, so that means it's going to change the y's. It adds 2 to the y coordinates. So we're going to, not with the x. We're going to add 2 to all of our y coordinates. Notice the x's stay the same. So this will be that, and this will be that, this will be 3, this will be 9, this will be 51. And since this is the inverse of what we started with, I'm going to flip the x and y backwards to get my new t-table. So now everything that was a y before is now an x and vice versa. Okay. So you flip the x and y's, and boom, this is our t-table that we're going to graph. Okay. So now I just have to transfer that. And using the miracles of modern technology, we can do that. Woohoo. And then you just graph that. Okay. 2.020, -2 is down here. 2.143, -1's right there, roughly. 3 zeros there. 9 1's a little bit out here, okay? Anyway, these logarithmic graphs should kind of look like, I don't know, they look like a sideways hook to me. Obviously, make sure your graph goes through the points, things like that, but they kind of look like a sideways hook, I think. So let me reiterate again what we did here. I flipped the x and y. I rewrote it so it was an exponential function, which I know how to make a t-table for, and then I adjusted that and switched the x and y back, okay? 22, write the expression as a single logarithm, okay. Remember, when you write it as a single logarithm, you deal with powers first, so any numbers that are out front now go back to being powers. That was a special property of logs. Let's see, 3 to the 5th is 243. Plus log 4. And then I remember if I have two logs of the same base and I'm adding them together, this adding is kind of like multiplying these two numbers inside the log. So we can actually make them a single log just by taking 243 times 4. So whatever that is, 243 times 4 ends up being 972. All they wanted was to get a single logarithm, and boom, we did it, okay? Powers first, then deal with the addition. And sometimes it might be subtraction, like here at number 23. Again, numbers out front of the logs, make them powers. So this will be natural log of m to the 5th minus natural log of n to the 3rd. Now, let's think about this logically. In the past problem here, addition became multiplication. Subtraction then would logically be division. So this will be natural log of m to the 5th divided by n to the 3rd. And are they in a single logarithm? You betcha. So we win the day. All right? I think we'll pause it there at the end of this page. So again, if you need me for anything, you can email me, tweet me, come into my room. I would be glad to help you with any of this. All right? We want you to do as best as you can on this final exam. All right? And I will see you folks later. Have a good one.